I said a few videos back that solubility equilibriums just like other equilibria. That means that Le Chatelier's principle still applies. We could add or remove a chemical, changing the concentration, which would cause the equilibrium to shift. We could change the temperature, and depending whether it's an endothermic or an exothermic dissolving process, maybe more or less would dissolve. Changing the volume and pressure doesn't impact it because there's no gaseous components as we're looking at these. But an important thing that can come up, kind of a trick with this, is if I take water away. If I take water away or evaporate it, we think about, well, my volume has gone down. And very often we treat that with the dilution equation. We think about when my volume changes, a lower volume means I have to have a higher molarity. But remember, with solubility, we already have the maximum amount of these things dissolved. So evaporating it just means more solid will form, and the molarity of the ions will actually stay the same. When we have solid at the bottom, if I dumped more water in and I thought about my molarities, once again, we'd often think about watering it down. But depending how much solid we have, we likely still have the same amounts or the same amount of dissolved ions. Now I have a larger volume, so more of my solid can dissolve. I have lowered the molarity, so more can dissolve. It's only going to dissolve up until it gets to that molarity. So you have to read the question carefully because there's a good chance where it's going to talk about that there's still solid after we've added the water. That means that we still have the same molarity of each of the ions, even though we may have less solid. So right here, adding or removing solid doesn't really shift the equilibrium. Adding or removing water keeps us at the same equilibrium probably, although there may be some change. But putting more of an ion in definitely has an impact. That ion we call a common ion. So a common ion, very simply, is an ion that already is a part of our equilibrium. So when we are taking silver chloride, the example we looked at before, a certain amount can dissolve in pure water. If I put it in salt water, there's already sodium ions there and chloride ions there. When I'm doing the calculation and when I'm looking at the effect of that, I have more chloride, one of my products, that causes me to shift left. That makes more solid or means that less of the solid can dissolve. So the common ion increases the concentration of that ion, causing the equilibrium to shift left to consume it, meaning that less of the ions or the ionic compound will actually have a lower concentration there. Any other ion, and an important thing, like if we're talking about salt water, which we could assume is just sodium chloride, if I added calcium fluoride to it, sodium is not a common ion, chloride is not a common ion. Those don't impact the solubility of this one. So it's really important that we're talking about this from a Le Chatelier's principle sense. Am I impacting one of the concentrations of the ions involved in the reaction? The acid-base unit that we have dabbled in maybe a little bit in first year and talked about with reactions is coming up and has a lot of equilibrium with it as well. And that impacts our pH. So when we have a solution that has hydroxide ion or technically even hydrogen ion, but most of the time it's going to be for this hydroxide ion, when I have a high pH, that means that I have extra hydroxide in my water. So a common ion is when I look at my solution and look at the two ions, magnesium hydroxide, if there's already hydroxide in the water, the magnesium hydroxide will dissolve less. If there's already magnesium in the water, the magnesium will dissolve less. We basically bumped those two things, one of those two things up, causing it to shift left, meaning less of those ions are able to dissolve as a result, which is the way we apply Le Chatelier's principle to solubility.